Hello, I'm Jonathan Aldrich, and today we're going to talk about LL parsing. So parsers are language recognizers. We saw how a context-free grammar can be described as a way to generate a context-free language. What a parser does is it goes the other way around. If you give it a program, in this case, then it will recognize whether that program fits the language or not, and of course, tell you about the structure of your program. It turns out there is an infinite number of grammars for every context-free language. So, any language that you could describe for a computer language, there's an infinite number of grammars for it, but they're not all the same. They're not all equal. So, for example, you might want it to be unambiguous how you parse something, right? We looked at ambiguity in a previous lecture. Also, some grammars might be more understandable than others, and therefore easier to work with as a compiler writer. Finally, some grammars might perform better in terms of parsing. So let's look a little bit at this last issue, parser scalability. It turns out that any context-free grammar that we have, we can create a parser that runs in O of n3 time. So in cubic time, in terms of the number of the size of the input, right, the number of characters, the number of tokens, we can parse that context-free grammar in cubic time. So for example, generalized LR parsers are a kind of parser that can parse any grammar in O of n3 time. Unfortunately, O of n3 time is clearly unacceptable for a parser and a compiler. It's too slow because we sometimes want to parse fairly large files, right? And so taking a large size and cubing it, even on a fast modern machine, is something we probably don't want to wait for in a compiler. It turns out some real languages do in fact use these GLR parsers, which have O of n3 time, but typically those languages have a grammar that's mostly in the LR class, which is one of the classes we'll study. And so in practice, they run faster than cubic time, even if cubic is the worst case. Fortunately, there's large classes of grammars for which we can build parsers that run in linear time. The two most important classes are called LL and LR. And they stand for the order in which we process symbols as we parse, which is going to be left to right in both cases. So that's the L. Both LR and LL start with L. But then there's two approaches. One captures the leftmost derivation of a particular parse tree, and one captures the rightmost derivation. So this is a little bit technical, but let me give you an example to show the intuition. So here we have a simple calculator grammar, just a subset of the grammar we've been looking at. And we'll take the same example we looked at before, the equation of a line, right? Slow times x plus the intercept. Now, given a particular parse tree, and this will be the parse tree we want, right? We talked about ambiguity, but let's say we've resolved that ambiguity, and we're going to parse it in the usual way, right, where multiplication binds faster, binds more closely than addition. We can still parse in two different orders. In fact, perhaps more than two different orders, but we'll just look at the leftmost derivation and the rightmost derivation. So in the leftmost derivation, what we're going to do is we're always going to choose the leftmost non-terminal to replace each time. So for example, we will start by taking a top-level expression and dividing it into expr, op, expr. And then we have two choices, right? Or three choices, actually. We could derive the first expr, or the op, or the next expr. Now, I've underlined in the leftmost derivation the leftmost expr because that's the one we're going to expand. So we expand that into another expr, op, expr. Once again, we're going to take the leftmost symbol and expand it. And so we'll expand the expr into an ID. Now, ID is a terminal, so we take the leftmost non-terminal, and that will be the op, right, which will be times in this case. Then we'll do the expr, and so on, right? You can see how the underlined symbol goes from left to right, and so that's the leftmost derivation. In the rightmost derivation, we're always going to choose the rightmost non-terminal to replace. So we're going to kind of do working at the other side, right? Instead of working at the beginning to parse something, we're going to work at the end. And so once again, we have no choice. We have to start by because we have only one start symbol, expr, we have to turn that into expr op expr. But then we have a choice, and we'll choose the rightmost of the three non-terminals, right? Expr op expr, right? So that right-hand expr turns into an ID, and then we do the op, and then we do the expr on the left into expr op expr. Then we take the rightmost of those two exprs and turn it into another ID. We turn the op into times and the expr into another ID, and then we're done. Notice that both of these derivations produce the same tree, but they focus on different parts of it as they go about producing that tree-like derivation. So LL and LR parsing, they start with this view of, do we start with the right-hand side or the left-hand side when we choose productions to explore? But they end up also working in different ways intuitively, right? So LL parsers are often called top-down because we kind of pick the first thing and divide it down. They're also called predictive parsers because they predict what we're going to see. Whereas LL parsers are called bottom-up. So they're going to work from the end and find small expressions and then build them up into larger expressions. They're also called shift-reduce parsers for technical reasons that we'll see in a future lecture. So there are several important subclasses of LR parsers, actually, SLR, LALR, and LR, in increasing order of complexity, but also expressivity. So LR are the most expressive parsers you can get. They're also more expressive than LL parsers. So see the text for more detail on the differences. We won't be talking about that in this lecture, but there are some interesting characteristics there. Now, when you describe a parser, you will often see LL or LR written with a number in parentheses, so something like LR1 or LL1. This number represents how many tokens of look-ahead are required in order to parse. So we're going to know where we are in terms of breaking down the top-level symbol into pieces, but we're also going to look several tokens ahead to figure out which production to use next. And typically that's going to be one token, right? So most real compilers use just one token of look ahead. Some tools let you special case to look further ahead for certain constructs. The expression grammar with precedence and associativity we looked at before is in fact an LR1 grammar, but it's not an LL1 grammar, and we'll look at how to make that change. An interesting fact is that every context-free language that can be parsed deterministically, which is certainly most of the languages of interest, has an SLR1 grammar, right? And as from this previous slide, SLR1 is a particular characteristic of LR1 grammar. So what that tells you is that LR grammars are very general. They're a little bit more complicated though, so we're going to start by talking about how to parse LL grammars. Let's start with the following simple statement grammar. So it turns out this is not actually an LL1 grammar, but we'll see how we need to adapt it. So in this statement grammar, a program is a statement list followed by the end token, which we denote as $3 signs. A statement list is a statement followed by another statement list, or it's the empty statement list. And then we have four kinds of statements. We can assign to an identifier, we can read an identifier or write an identifier, and we can call a function. And then, of course, if we call a function, then there's an identifier list, which has this recursive structure. So let's look at how an LL parser might work on this grammar. We'll encounter a problem, and then we'll see how to solve it. So let's parse this simple program. We're going to read A, process A, and then write A. Simple program. I've shown you the grammar here on the right. And here's the parse sequence. So we start with the program, right? LL parsers are top-down, so we start with the thing we want to find, a program. And then the only thing we can do with the program is break it down into a statement list and the end symbol. So we do that as the next step. Now a statement list can either be empty or it can be statement, but we don't have the empty program here, right? We have a program that starts with read. And so we have a look ahead of read, and that tells us, okay, there must be something here. It's not the empty statement list. Let's go into statement and figure out what's next. Now statement has four possibilities. And our look ahead is still read, right? We used read to figure out to go from statement list to a statement, but now we'll use read to figure out what kind of statement we have, right? And so we'll use the second production of those 4 statements, and now we have broken the statement into a read ID. And then we still have the statement list, which is going to be the future, right? So our list expresses the tokens we expect to see and the higher level constructs like statement list that we intend to see after we've read those tokens. So now we'll read a couple of tokens. We'll accept the read and ID tokens. And now we have more statements to read. So at this point, things are a little bit more complicated. So process is going to be an identifier. And if we just look at process, then we can't tell, are we assigning to a variable called process, or are we calling a function called process, right? Now, if we were able to look ahead 2 tokens, I could tell you, right? Then that it's a function call. But right now, I can't tell you. And so there's an ambiguity in this. There's an ambiguity in this grammar. We can't tell what to do at this point when we get the ID look ahead. So if we want to parse with an LL1 parser, then whenever we make a choice between 2 productions of a non-terminal, we have to be able to predict which one is taken based on one look-ahead token. And we can't do that with the grammar that I showed you. So we have to change the grammar. There are 2 basic problems that you commonly see with grammars that make them not be LL. So one is called common prefixes, right? And the idea here is that a statement can start with ID, and there's 2 different productions that start with ID, right? And so that's the basic problem. What we can do is we can left factor, okay? So we can turn statement into, we can make statement have just one production that starts with ID, right? It might have other productions that start with read and write. I'm not showing those here. But we take these 2 productions to start with ID, and we'll start with ID, and then we'll have the tail of an ID statement, okay? So an ID statement is whatever comes after the ID. And now there's 2 possibilities which start with different tokens, right? So there's the assignment possibility where we complete the ID statement by assigning to an expression to that identifier. And then there's the call case, right? The call production where we pass in a parenthesized list of arguments. So this is called left factoring. We're factoring the 2 kinds of productions that start with the same symbol into one production. This can actually be done completely mechanically. So that's nice, right? Tools could potentially do it for us, but it's also, something you can do yourself fairly easily. Another slightly more subtle problem is called left recursion. It's another thing the LL parsers can't handle. So let's look at this example, right? We have an ID list, and an ID list is either a single ID or it's an ID list that's followed by another ID, right? So this is called left recursion because the second production here, right, the second option here is ID list is an ID list followed by an ID. And ID list is defined in terms of itself. On the left-hand side it's like the first symbol on the right-hand side of that production, right? ID list is an ID list followed by an ID. And so what's going to be confusing to the parser here is that an ID list can start with ID, but there are 2 cases, right? The ID list can just directly start with ID because that's the whole production, or it can start with an ID list which also has an ID first, right? And so we can't tell which case to do. So what we're going to do is again refactor this so that an ID list starts with at least one ID, and then instead of using left recursion, we're going to use right recursion. And so the recursive thing will be an ID list tail. That's whatever follows the ID, since every ID list starts with an ID. And then the ID list tail is defined as, okay, we're going to put a comma and then an ID and then another tail. Or it can be empty, right? Because if we just have one, at some point the list has to end. So again, we can get rid of left recursion mechanically in any grammar. You might think that this is enough, but it turns out that eliminating left recursion and common prefixes doesn't necessarily make a grammar LL. There's infinitely many languages that simply cannot be parsed with any LL parser, and you can apply these mechanical transformations, but you get some other grammar that's also not LL for those languages. For the few that arise in practice, however, there are some workarounds, right? A common workaround that you see in some of the tools that are based on LL parsing is that you can write a little custom function that looks at future tokens and decides which production to use when you have an ambiguous case. So That's a little outside the theory. It's a little bit of a kludge, but it is a solution. It is a practical solution that gets used in production, compilers a fair bit. We don't have to do that in this case, though. We can just refactor this grammar. And so here is an LL1 version of that same statement grammar, right? Now we have these tail constructs, both in the statement case and in the ID list case, referring to the two operations I saw before. So armed with this, we can now go ahead and continue our LL parsing example. The first part actually used grammatical productions we didn't change, so I'm going to leave that out, right? Those are things you already saw. But after we accept the read and ID tokens, we'll observe the ID look ahead. We will determine that there's another statement coming. And now the statement will be refined according to our new production into an ID followed by an ID statement tail. And so we will read the ID token, and then we figure out what the ID statement tail is. In this case, there's no comma, so we won't be reading any more arguments. We'll take the, ID statement tail. There's two options, the assignment option and the function call option. The token we see is the open parentheses, and so that tells us we're in a function call case. We go into there, we accept the parentheses token and expand ID list, as there's only one production for that, right? So I kind of took two actions right there. And then we'll accept the ID token, and now the ID list tail is going to be empty, right? There's no comma, and so based on the parentheses look ahead, we're not going to see any more IDs in the ID list, and so we have to just reduce it with ID list equals empty. We then accept the parentheses, and we're ready to accept the last write statement. So I'll go through this fairly quickly, right? We'll expand the statement and to a write statement. We'll accept the two tokens write and ID. We'll discover that there's no more that we now just have the end of file token, and so we accept the statement list, and now we're done. All right, so hopefully you now have an intuition for how LL grammars work. Let's do an exercise. Here I've given you a simple grammar for a very simple expression form, and go ahead and try using the refactoring techniques to turn this grammar into an LL1 form. Once you've done so, then think about some of the advantages and disadvantages of the new grammar that you produce, which is LL1, compared to the original one that I'm showing you here, which is LR1. Okay, here's one solution to the problem. You can see we've used the tail technique and left factoring and elimination of left recursion in this grammar. In terms of this grammar compared to the other one, these are subjective kinds of things, and maybe your answer varies from mine. But what I would say is, like the bottom-up grammar, here we capture associativity and precedence, but most people probably don't find it as elegant. Perhaps you would agree. For one thing, the operands of a given operator aren't in a right-hand side together, right? We've separated. If we have one term plus another term, we've separated that into an expression and an expression tail. So the grammar is not quite as pretty, but the parsing algorithm is actually quite simple, and it'll be easy to implement, as we'll see in the next lecture. And so a lot of people feel that this makes up for the weakness. Next time we'll talk about implementation. See you then.